So in the previous example and in the previous section, we looked at this polynomial f of x, and we found its critical points. So we found one at x equals -1 and another at x equals 2. And we saw that those corresponded to this local maximum and this local minimum, right? So these critical points let us know where we might find a local max or a local min. What it didn't tell us, what critical points don't tell us, is whether this should be a local max or a local min, right? We can see what they are from the graph, but if we didn't have the graph, we wouldn't know whether x equals -1 or x equals 2 is a local min or a local max, or maybe they're both local mins, both local max. We don't know, right? So we can use another observation to determine whether a critical point is a local max or a local min. Okay, so if we think about these two sentences right here on the bottom, so we can observe that if we have a local maximum, then it should be that the function is increasing to the left of that local maximum, right? So for example here, you can see the function is increasing to the left of that. And then it should start decreasing to the right of that local maximum. Right? So we can see to the right of x equals -1, we're decreasing. Okay? So if my function is increasing to the left and decreasing to the right of a critical point, then we should expect that that point is going to be a local maximum, right? Because it goes up and then down. Okay? If we're looking for local mins, then we can see that if the function is decreasing to the left, right? So for example, like here at x equals 2, we're decreasing to the left and then increasing to the right, then my function should be going down and then up. And if you think about that, that gives you a shape that looks like it's got a local minimum. Okay? And remember, we have a tool for figuring out whether a function is increasing or decreasing. And I'm hoping that you took the chance to play around with this link, right? It's the same one that we had before. And we can see that slopes of tangent lines are positive when the function is increasing and negative when a function is decreasing. Okay, so if we look at this graph, so here is the polynomial that we were talking about, or actually this is a different polynomial. So here's a polynomial, right? I drew it here in red, and I took its derivative, right? So its derivative is right here, and I drew it here in gray, right? So you can see this is a parabola, so here's that parabola, okay? So we can determine not only the critical points of this polynomial in red from the derivative, but we can also determine whether these critical points are local max or mins by looking at where the derivative is positive and where the derivative is negative, right? Because that tells me where the function is, the polynomial is increasing and where it's decreasing, and that can help me figure out what the shape of the graph is looking like, so whether it should be a local max or a local min. Okay, so if we think about the critical points, right, the critical points to the polynomial in red should be where the derivative is equal to 0. And you can see right here, the derivative touches the x-axis, so the y value there is 0, right? So the derivative is equal to 0 at those points. And if you trace those up to the function itself, you can see those do give you these points where we have local max or a local min. Okay? But we don't really know, if we didn't have the graph in red, we wouldn't really know whether those critical points were giving us local maxes or local mins. So we can use the derivative to tell us whether the function is increasing or decreasing. And then we can use that to figure out whether it should be a local min or a local max. Okay? So if you look at the derivative, right, and we're trying to figure out where is the derivative increasing, or not the derivative, so where's the polynomial increasing, right? So then we're really looking at, okay, this section right here. This is the part of the polynomial where it's increasing, and that corresponds to where the derivative is positive, right? So see there, it's above the x-axis, okay? We might also figure out where the polynomial is decreasing, so that would be right in this area, and then again in this area, right? Starts going down here. And if you look at the derivative, precisely in those areas, the derivative is below the x-axis, right? It's negative. Okay? So if a function is increasing, we can expect the derivative to be greater than 0. And if a function is decreasing, we can expect the derivative to be less than 0. Okay? So we're going to use that to figure out whether a critical point is a local maximum or a local minimum. Okay? So the first derivative test is really just a summary of what I just said, right? If the derivative is greater than 0, then we expect that the function will be increasing. And then if the derivative is less than 0, we can expect that the function will be decreasing. Okay? So in addition to telling us where the function is increasing or decreasing, we can use derivatives to tell us something more about the shape of a function, right? So in particular, we can use derivatives to tell whether a function is concave up or concave down. So that's a couple of definitions down here. So if we look at the definition for concave up, so a function is concave up if its derivative is increasing. Okay, so a function f is concave up if f prime is increasing, and a function is concave down if its derivative f prime is decreasing. Okay, and the points where a function switches from being concave up to concave down, or vice versa, from concave down to concave up, those points where the switch happens are called inflection points. Okay, so in less technical terms, right, so what does it mean for the derivative to be increasing, for derivative to be decreasing? So in less technical terms, if we just looked at a graph, a function is concave up if it bends upwards like this, right? So you can see something like a polynomial or a parabola facing up that bends upwards, it cups upwards, right? That's a function that's concave up. And something that's concave down, right? It's bending downwards like this, like a parabola facing down. That's something that's concave down. Okay? So we're going to see a further explanation of this, right? So if we look at this graph in pink, we can see the intervals in which it's concave down, right? We've labeled those already. So maybe let's highlight those. So concave down. So if you look at this section of the graph, the function is concave down there, right? It's cupping downwards. It's concave down again on this interval right here, right? It's facing downwards, cupping downwards. And then it looks like it happens again right here, right? It's facing downwards. Okay. The function is concave up from here to here, right? It's cupping upwards like a parabola facing up. It's concave up again here, and then a concave up again here. Okay. So one thing I want to point out is the inflection points, right? So here, the function switches from being concave down to concave up. Right here as well at C, the function switches concave up to concave down. Right here, once again, we see a switch, and right here we see a switch again, right? So notice this point at E, that's not an inflection point because it's concave up on both sides of that point. Right? So that's not an inflection point. Okay, so these points in pink are inflection points. Okay, so those are all in pink. Okay. We can also maybe write down what the local maxes and mins are. So you can see there's a local max somewhere right here, a local min right here. This point in D also happens to be a local max, so maybe I'll do something like that. This is a local max. We have a local min somewhere right here. And then these two endpoints look like they're local mins as well. Okay, so one thing I want to point out is these points right here. So at D and at E, there's a very sharp change in the graph there, right? So those are points where the derivative does not exist. Okay, so if we were looking for critical points, we would get these, so these critical points from where the derivative doesn't exist, right? So we shouldn't expect that the derivative equal to 0 is going to give us those points because they're very sharp cusps, but we will get those from where the derivative doesn't exist, right? All of the other max and mins we could probably get, or we can get, from f prime of x equals 0, okay? So if we try to get this down to a test like we did with the first derivative test, if we're looking for where a function is concave up or concave down, so where is a function concave up? Well, by the definition, this means we're looking for where the derivative is increasing, Okay, so that's what we defined concave up to mean. Derivative is increasing. But if we think about it, a function, so in this case the derivative, is increasing when its derivative is positive, right? So now we're talking about the derivative of the derivative, right? So if f prime is increasing, we should expect that the derivative of f prime, so f double prime, should be positive, okay? So this tells me if I'm looking for where is a function concave up, I'm really looking for where is the second derivative greater than 0. Okay? Now, if I'm doing the same thing with concave down, well, concave down meant that I was looking at a derivative that was decreasing. A function is decreasing when its derivative is less than 0, right? So that means f prime is decreasing when f double prime is less than 0. Okay, so I should look for a second derivative less than 0 if I'm looking for when a function is concave down. Okay, and that's precisely what the second derivative test says, right? So if the second derivative is greater than 0, then the function will be concave up. If the second derivative is less than 0, then the function will be concave down. Okay, so this tells us something about the shape of the graph.